Hello everyone, this is Dr. Doug, and in this video I'm going to introduce you to enthalpy. And so we're going to talk about some energy, we're going to talk about exactly what enthalpy is and how it relates to chemical bonds. So first remember that, right, when we have a chemical reaction, we have two things that occur here, right? One is a rearrangement of atoms, and so if I give an example of a chemical equation, right, like let's say we're talking about burning methane, the idea is that I take those chemicals, right, I take those molecules and I react them together and I rearrange the stuff, right? So now my carbon no longer has the H's, it has oxygen, and now the oxygens are not by themselves, now they're with the water and the oxygen. And you probably remember that we got to balance these things, so I'll put in some coefficients to make sure it's all balanced. And that's what we're talking, it's part of a chemical reaction, right? It's the fact that you rearrange atoms. We're going to break and make a lot of bonds. And when we start talking about enthalpy, that breaking and making bonds is going to come back and be really important. So in addition to rearranging the atoms in a chemical reaction, we also see a change in energy. And energy is kind of hard to define because it's a little nebulous, but generally we kind of understand energy as being something that can do work, right? Where work is the idea that you apply some sort of force over a distance. And that would be something like, imagine like an engine of a car, for example, right? You're doing work when you burn a fossil fuel in your engine, and it expands, the gas expands and moves the piston, which helps you move your car. That would be an example of work, or anything that kind of moves something. That's what we're talking about with work. That's not the focus of this particular video. This video is going to focus mostly on heat, which is the other kind of thing that energy can do, which is cause a change in temperature. And by a change in temperature, I mean it can either increase the temperature or decrease, either way. So increase or decrease. Either way. And so we're going to talk about a lot of our reactions can either release energy, release heat, or absorb heat, or require energy, right? So we're going to talk about these changes in energy in terms of heat, primarily for the reactions that we're looking at. Now, the units for this energy that we're going to talk about are going to be calories. Calories you've probably heard of. This is calories with a little c, where the definition of a calorie here is the amount of energy required, so the amount of energy required to heat 1 gram of water, 1 degree Celsius. And it's a little more specific about what degree, but basically that's what a calorie is. It's the amount of energy required to heat 1 gram of water at 1 degree Celsius. Now, again, you've probably heard of a calorie before, right? You look on a food label, it says how many calories there are. Just as a side note, that's a different kind of calorie. It's related, but it's different. The food calorie, so I'll just make a quick note here, the food calorie, which has a capital C, not a lowercase c. It's kind of a ridiculous difference, but it's a difference. A food calorie is actually 1,000 calories. Or in other words, it's a kilocalorie. It's 1 kilocalorie. So a food calorie, right, if you eat something and it has 120 calories, what it means is it has 120,000 of these calories over here, right, that you could heat 120,000 grams of water, 1 degree Celsius is the idea. So when we talk about calories, it's actually a pretty small amount of energy, and so we often talk about kilocalories because that's a more reasonable amount of energy. But that's how we're going to talk about this change in energy. We're talking about it in terms of heat. We're going to talk about it in terms of calories. So let's figure out a little bit more like how that fits in with enthalpy. So enthalpy is just the change in energy due to making and breaking bonds. And I put also here, or attractive forces. Same idea, right? They're like a bond. So the change in energy due to making or breaking bonds, right? Every time you make a bond, we're going to see that you release energy. Every time you break a bond, you're going to require energy. You're going to absorb heat that way. And enthalpy is abbreviated as an H. So that's kind of annoying. It's not abbreviated as E. E is just energy generically, but enthalpy specifically is H. So what I want you to do is kind of think with me about this example here, right? So let's look at this example where I have, actually let me do this in black. Let's look at this example here where we take the simplest of atoms, just hydrogen, and they're going to combine to make the simplest of molecules, an H2 molecule. Whoops. just an H2 molecule, right? So here I have the atoms versus the molecule. And I'll even make a little note here, right? These suckers are atoms. This is the molecule. And so my question is, right, and we've asked this kind of question before, which side of this equation is more stable? Where are these things going to end up? Where do they want to be? And I'm using sort of these anthropomorphic terms because it helps us kind of think about where things want to be, right? So we talked about just atoms alone here, right? So I've got a hydrogen, it's got one valence electron, that's it. And the question is, why would two hydrogen atoms want to join together to form a hydrogen molecule where they're now sharing those electrons, right, making a covalent bond? And if you remember, right, we had something called the noble gas rule, where we said that everything wanted to look like the nearest noble gas. It wanted to fill its shells and have kind of more electrons, generally speaking. And so here, right, now each of these two hydrogens have two electrons, right, because they're sharing electrons. They have two electrons in that innermost shell, which could only hold two electrons, so they've got a full shell, which is nice. Plus, they look like helium, which is their nearest noble gas, right, or in other words, they have two electrons. So if I look at these, if I compare these two sides here, right, these are a little bit unhappy, right? They're a little unhappy, and that's because they do not fulfill the noble gas rule. Also known as the octet rule. Right? Whereas if we go over here, these are happier. And that is because they do fulfill the noble gas rule. Right? Because they do fulfill the noble gas rule. Right? They look like helium. It looks like they have two hydrogens around them, right? Remember that line represents two electrons. So then if I'm asking myself which one is more stable, right? I've got the unhappy one and I've got the happy one. Which one's more stable? Or in other words, which one's more likely to stay the way that it is? It's going to be the happy one, right? But the one that's already happier the way that it is more likely to stay the way that it is. Or in other words, it's more stable. So here we're going to have something that's more stable, whereas the actual hydrogen atoms themselves, where they're separate, they only have one valence electron, those are less stable. Right? Because they don't want to stay the way that they are. They want to do something, they want to react with something to either give away an electron, to take an electron, to share an electron, something so that they can achieve that noble gas-like state, or they have their full shells. And then our last kind of translation thing that we have to do here is ask ourselves, well, what does that mean in terms of energy? Which one has higher energy? Which one has lower energy? And remember that energy is the ability to do work or to transfer heat. And so which one do you think is more likely to be able to do some work, or which one's able to transfer energy? Is it the one that's happy and stable the way that it is, that doesn't want to change? Or is it the one that is unhappy and does want to change, the one that's less stable? So the one that's more likely to be able to do work or to change the temperature of something is a thing that is not happy the way that it is. Or in other words, a thing that is less stable. So we'd say this is less stable and that this has higher energy. And that's going to be really important versus the one over here has lower energy. And these concepts will always go together. If something is less stable, it always has higher energy. If something is more stable, it always has lower energy. Always. And we can represent this. This is kind of a lot of words to just be like, oh, hey, the right side is better than the left side, or the right side is happier than the left side. But what we want to kind of translate to, and I'll do a video on this later a little bit more, is talk about, we can represent this in terms of an energy diagram. So I can draw, you'll start to see lots of these. These are called energy diagrams, where over here you have energy increasing. So let me write this. So energy diagram. And we can represent this graphically by saying, right, so I can say, okay, well, I've got my two hydrogen atoms, and they're going to turn into an H2 atom. And the axis over here, this is just the reaction coordinate. This is like the progress of the reaction. So reaction coordinate. It's not time or anything like that. So it's the reaction coordinate. The idea here is if I'm going to put my H2s somewhere, right, we just said that my H2s need to be relatively high in energy. So I'm going to have it up on this, high on this scale. So I'll put the H2s here. Oh, sorry, the two hydrogens here. So hydrogen and hydrogen, those two suckers. Versus the H2 we said was lower in energy, so I'm going to have it as a lower level. I'll put my H2 down here. And to complete the energy diagram, all we do is we connect those two. And there'll be a little hump and stuff, and we'll move it down like this. We'll talk more about what that little hump means. We'll talk more about going uphill or downhill in a future video. But this is a way we can represent this reaction, is saying that, oh, it starts off higher in energy, less stable, and in the end it becomes lower in energy or more stable. And so we have this energy diagram. And what happens is, as you move from this energy down to here, you release energy, is the idea. So as you go from a high energy to a low energy, you release energy. You release energy. You go from some high amount of energy to some low amount of energy, right? It's kind of like rolling a ball down a hill, right? If you have a ball high up on a hill and you roll it down to the bottom, you're releasing energy, and that energy gets transformed into like motion or kinetic energy or something like that, right? So you're going to release energy. And what we're going to see is that always, always, always when you make a bond, right, which is what we did here, we made a bond, you always go downhill, you always release energy. So right, remember that your enthalpy is a change in energy due to the making or breaking of bonds. And what we're going to see always is that when you make a bond, anytime you make a bond, you always are going to release energy. Or in other words, we're going to come back to this more, but the change in your enthalpy, the delta H, the change in enthalpy, is always going to be positive. Or sorry, is always negative. It's going to be a negative value. And I'll show you more about that when I talk about the energy diagram video. Whenever you make a bond, you always release energy. The delta H is negative. Always, always, always. Now, whenever you break a bond, you always absorb energy. You always absorb energy. You always absorb heat. Yeah, so here, remember, we're talking about the heats, change in heat, change in temperature. And so your delta H is positive. Whenever you absorb energy, your delta H is positive. Now this, I mentioned that this is heat. Whenever you make a bond, you release energy. The idea is that this always feels warm. If you were to do a reaction in your hand, this feels warm. So this is like something catching on fire, for example. It feels warm. That's exothermic. That releases energy. Whereas if something breaks a bond, you absorb energy, and delta H is positive, that feels cold to us. So if you've ever felt like one of those cold packs, for example, that's what we're talking about. And I mentioned those terms, right? When you make a bond, whenever you release energy or anything, that's called exothermic. You're having heat leave something, versus any time that you break a bond and you absorb energy, that's called endothermic. Let me write this down here, fix this. That would be endothermic, right? So whenever delta H is positive, that's endothermic. It feels cold. It absorbs energy. And this is always, always true. Sometimes you hear biologists, for example, mix these up when they talk about like ATP turning into ADP. Breaking that bond does not release energy. Breaking any bond always absorbs energy, always requires energy. So we'll go into this in a little bit more detail in the next video, which is about energy diagrams and more about these changes in energy. So hopefully you have a little bit better idea of, right, the fact that there are energy changes in a reaction, and that energy can be used to either do work, which is a whole other topic, or it can be used to change the temperature of something. When you're talking about those changes in heat or changes in energy, that's enthalpy, and that's due to making and breaking bonds is the idea. So making and breaking bonds releases heat or requires heat. If you have any questions or comments, leave them down below. Study up. Please watch the next videos on energy diagrams.